Hi, welcome back. On today's lecture series, we are going to discuss about optimal operation of generators. So for this, we have to use the design thinking principle. So the first one, we have to empathize. So before proceeding this optimal operation of generator, so we have to list out the companies which are generating electricity because in day by day the fuel cost is always gets rising and every rupees we have to save on generation and the grid operators. So here we have to must balance the demand and the demand as well as the generation across 24/7. And the end users, it should have the demand should be affordable and it should be very reliable and it should be uninterruptible power supply. And according to the environment, the excess generation, it gives excess emission and the fuel is gets wasted. So these are all the few topics to empathize. And based on the empathize, we have to define. So how we have to decide in order to meet up the demand. So in this regard, which generator has to be turned on, which generator has to be turned off, and what is the output level of each generator, and what is the sequence we have to follow to turn on the generator in order to meet the demand at minimum cost without violating any technical limits. So here we have to follow some key constraint like the generator capacity. It should be between the minimum power and the maximum power. It should not violate the limit. And also the ramp up or ramp down rate. It should be one of the constraint. And we have to note down the transmission line limit. So what is the capacity of electrical energy transmission from one end to another end, and here we have to maintain the system frequency of 50 Hz in order to for grid synchronization. And also we have to ensure a reverse margin requirement for immediate requirement purpose, etc. So here in this ideate part, we are taking the total power demand and it will be committed to the n number of generator. So this is mainly to minimize the total fuel cost. So for this we may take in solar power or it may be in wind power, whatever it may be for different cases. So we have to compare with the equal incremental cost and based on the time rate. So if we are having more number of wind energy or the potential of power to generate the electricity from the wind energy, so during that time we can use the wind electric power system. So to generate the electricity, so during that particular time we may able to minimize the generation from the thermal or it may be in a nuclear power plant to save the energy or to save the fuel cost. So this is the cost function of generator. It may be in quality cost curve and also it should meet out the incremental cost, and we have to face some penalty factor because in account of transmission losses, the distance generator is gets penalized. Okay, so here if you are increasing the generation, automatically the incremental cost is also gets increases. That is the thing, but for every hour we are getting the curves. So it is just like in quality cost curve. So here we have to follow an unit commitment for the optimal operation of generator. So in the unit commitment here we have to forecast the load. What is the load forecasting for unit 5 o'clock or unit 10 o'clock or maybe early morning 6 o'clock like that. So first of all we have to forecast the load, and second one we have to rank the units. We are having n number of generating units, so among that we have to prioritize the ranks, and based on the rank we have to commit the unit has to be turned on or it may be turned off, and then we can use the economic dispatch in order to meet out the minimum operating fuel cost. So here we may use the simple priority list method, or it may be dynamic programming, or it may be full load average production cost to determine the cost. And the constraint in generator operation. So here the constraint, the generator limit, it should be between the minimum and maximum value. It should not exceed the value. And the ramp rate, it's also the maximum megawatt change per minute, which is used to protect the turbine blades. And also the minimum uptime downtime. The generator must be stay on for a minimum hours after switching. Also, the generator must be off for minimum hours after switching. This is to save the cost. And the spinning reserve, the extra capacity on standby, typically 10 to 15% of demand load can be prepared. So this is certainly if the load is increases, the spinning reserve can be used for the compensation. So for this, we can use the optimal power flow. That is nothing but a network constraint. So the main objective, minimize the total generation cost. So for that, that is a main objective. So for this, we have to balance our equation. So that is nothing but, and the total input power is equal to total demand plus losses. And here we have to maintain the network limits, the bus voltage, line flow, that is like a real power, reactive power, and the angle differences within bounds. Everything can be limited in the network limit. So for this, we can use the either Gauss-Seidel, Newton Raphson, interior point, or some of the methodology can be used to analyze the optimal power flow. So this is solving a two generator economic dispatch problem. So these are the certain given data will be there. So by using the formula or by using the step-by-step procedure, by determining the lambda, and you have to use the power balance equation, and we have to determine the generator power for 2 units, and we have to check the limits whether in within the limit or not, and so that we can able to determine the cost. We have to check this. And we have to validate does the optimal dispatch is working or not. So what is the amount of cost per sale? So everything can be discussed in this here. And this is a real-time applications. It can be used for the national load dispatch, and also it can be used for the renewable integration like solar, wind, to maintain the grid stability, and some of the generator bit-based incremental cost for electricity markets. And this is a mind map. So here we have to empathize, to define, and we have to you can use the various types of economic dispatch and unit commitment problems. So this is one of the question. Here, the solar panel have zero fuel cost. That is constraint A, B, C is 0. What happens to the equal incremental cost criterion when renewables are added to the dispatch problem? Should lambda is equal to 0? So if you know the answer, just to put in the comment section. And this is another assessment. Here the condition for optimal economic dispatch among n generators. Here we have to neglect the losses. So whether it may be equal power output or equal incremental cost lambda or equal average cost D or equal fuel consumption. So if you know the answer, just you can put in the comment section. These are the few textbook and reference books can use for these topics. Thank you.